So today we talk infinite series, which is the sum of an infinite group of numbers. As you can see below in the example, I have a finite set of numbers here, which adds the numbers from 1 to 51 in order, and then stops. The infinite series is notated by the dot 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 at the end with no terminating numbers, which means I add the numbers from 1 to infinity, which we know has no sum. Let's take a look at some infinite series. This appears to be an arithmetic pattern where my common difference is 2, and it adds the numbers from 7 to infinity, incrementing by 2 every time. And we know that if we're going to infinity, my last number is really undefined. Therefore, this would really have no sum because it would just keep going forever and ever and ever. If I take a look at a geometric series, this is a geometric series where my r is 2. Notated here, my ratio is greater than 1. And again, these numbers keep going on and on and on. And down the road, I will get to infinity. And if I'm adding infinity, it makes no sense because I can't really wrap my arms around that. Say this guy has no sum as well. Now this is a different look. We're looking at a geometric series. The ratio in this case is less than 1 though, so my ratio is equal to a half. And if we look at the numbers now, we start at a half and then multiply each term moving down the row by a half every time. My numbers start getting less and less and less and less. And as I continue down the road, my numbers are getting actually closer to 0. They'll never go negative because if I take a half of a positive number, it'll never go negative. So this gets closer and closer to 0. The question is this going to have a sum? And that's what we're going to look at today. One thing we can take from this prior demonstration is that if I look at an arithmetic series, none of those will ever have sums because they go to infinity. Likewise, for any geometric series where my ratio is greater than 1 in absolute value, that's going to also have no sum because we'll eventually go to infinity. Now, if we look at a geometric series where our ratio in absolute value is less than 1, I'm claiming that's going to have a sum. And we're going to take a peek at why this would happen by looking at our general equation for geometric series right here. So most specifically, we're going to want to look at this term, r to the n. And we know that if r is less than 1, then I'm going to raise some fractional value to the infinite power. So if I raise some fraction, we could call it 1 over, but let's call it like 99 over 100 to the millionth power. And that's not even close to infinite, because remember, I'm trying to add a whole bunch of these terms. This is going to be a ridiculously small number. In fact, r to the n, assuming that the ratio is less than 1, is going to go to 0. So if that just goes to 0, I'm going to be left with the first term. The only thing that's in this parentheses now is 1, so it's just the first term over 1 minus r. And that, in fact, is our equation for an infinite geometric series where r is less than 1. And you'll notice that we're not raising to any specific power in this case. So since the number of terms goes to infinite, that number of terms doesn't affect my sum. We'll see how this plays out in our next problem. So if I take this sum where I have a ratio of 1/10, then I say the sum is equal to the first term, which is 1/15, all over 1 minus my ratio. So in that case, I have a 15th over 9/10. And then we just multiply that on our calculator, and we find that we get a sum of about 2/27. And again, we can do this because my ratio in absolute value was less than 1. Now I take a look at the next series, and I want to make sure that that's geometric. And I look, and sure enough, if I multiply by -1/2, whose absolute value is less than 1, that is geometric. So I can use my infinite sum, stating that my first term over 1 minus my ratio is going to give me my sum. So this ends up being 3/8 divided by 3/2, which we know is the same as 3/8 times 2/3, or in this case, a fourth. So the sum of this, as I add forever and ever, is going to end up equaling a quarter. Now, again, you're probably asking, well, if I'm adding numbers forever and ever, how do I get a quarter out of that? Because I just keep adding and adding. It's a good question. Turns out that it's a really, really good approximation. The numbers get closer and closer to a quarter. It approximates it. If you think about that first example that we talked about, we had, I believe, a half adding to a quarter, adding to an eighth, etc., etc., etc. If I look at all those numbers and were to graph each one of them, those numbers will get closer and closer and closer to 0. So the numbers that you add end up being so infinitesimally small, they don't really increment your sum to an amount that will affect the final answer. It's almost negligible as you get lower and lower and lower. So we're going to do a little bit different problem that doesn't look like a sequence type problem or a series type problem, but we're going to change this repeating decimal to a fraction. Now, if you think about what a repeating decimal is, it repeats itself over and over and over again, and we know that. But let's look at what repeats and the values of each repetition. Well, if we take a look at the first one, we know that that is basically 15 over 100. And if we add the next repetition to that, that's 15 over 10,000. And the next repetition after that is 15 over, I believe it's 1,000,000, etc., 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 etc. So this, in essence, is an infinite geometric series. And we can say that our ratio in this case is 1 over 100, because we're adding a multiple of 100 every time. So I can then say that my first term in this whole thing was 0.15, or 15/100ths, over 1 minus my ratio of 0.01 will get me some sum. That's going to equal 15 over 100 divided by 99 over 100, or 15 over 100 times 100 over 99, which gets me basically 15 divided by 99 which is equivalent to 5/33. And that's my fraction equivalent to 0.15 repeating. And that's all we've got for you today. We'll see you tomorrow.